Okay, thank you very much for invitation. And excuse me, but I want to say a few words about my friend Vadim Malyshev, но на русском языке. Я с ним, с Вадимом, знаком с очень ранних лет. Не то чтобы мы часто встречались и дружили, но у нас всегда были темы для обсуждения, и, как мне кажется, мы очень сочувствовали друг другу в разных делах. Когда я думал, как бы охарактеризовать его личность, и в частности, как математическую личность, то я подобрал слово «отдельный», «особый». Он, находясь в центре математической общественности в Москве, семинаров и так далее, тем не менее, всегда был у него было особенное положение и свой взгляд на разные вещи. Это началось с его знаменитой первой работы, которая была опубликована в трудах Мехмата, по-моему, в конце 70-х или в начале 80-х годов. Вы слышите меня? Мой голос слышен?
Да, прекрасно слышим.
Вот, у нас были общие темы, причем даже много таких тем. У него была любовь к комбинаторике, как и у меня, причем к очень разной. Он любил, допустим, работы Татта, работы американского комбинаторика знаменитого, значит, который много занимался основанием комбинаторики. И на эту тему у Малышева был замечательный обзор, который, по-моему, в успехах, который до сих пор не потерял своей ценности. Кроме того, мы очень интересовались разными приложениями, и нужно сказать, что он часто бывал здесь, в Ленинграде, потом в Петербурге, поддерживал связи со мной и со школой Фадеева, и очень часто выступал у нас на семинарах и на математическом обществе. В общем, это очень большая потеря, и его биография тоже особая. Его работа во Франции тоже как-то выделялась от многих российских математиков, которые туда уехали. Он там занял очень прочную позицию, фактически руководил очень важной лабораторией, был признан там, это хорошо известно. Тем не менее, он вернулся и очень много работал, и в частности основал журнал, который, я надеюсь, будет существовать и дальше, и работал здесь. Словом, я очень сожалею о его кончине, он был моложе меня, тем не менее, так получилось. И вот я хочу сегодня свой доклад посвятить ему. Мне кажется, что тема его была бы, особенно конец моего доклада, был бы ему интересен. И теперь я перехожу на английский и хочу сказать, о чем пойдет речь. Фактически, главная тема моего доклада – это ответ на очень простой и старый вопрос в математике, на который, по-моему, до сих пор четкого ответа не было. А именно, что такое распределение функций нескольких переменных? Для одной переменной мы хорошо знаем, что, если отвлечься от кратности и считать, что функция все значения принимает с одной и той же кратностью, конечной или единичной, или даже континуальной, то единственный инвариант функции – это ее распределение. То есть некая мера на множестве ее значений, скажем, для вещественной функции это мера на прямой. И очень несложно восстановить с точностью до изоморфизма функцию по ее распределению. Совершенно другая ситуация для двух переменных. Мне кажется, что такой вопрос и поставлен был только лишь сравнительно недавно. То, о чем я буду рассказывать, это называется матричное распределение. Это и есть аналог распределения функции одной переменной, но я в основном буду говорить для двух переменных. Обобщение на многие переменные, разве лишь более громоздкое, но никаких сложностей после соглашения о том, что сказано про две переменные, не существует. Во всем этом будет играть роль, значит, на самом деле мы говорим о функции, которая задана на пространстве, прямом произведении двух пространств с мерой. Ну, например, на квадрате. Или, например, представьте себе, это главный пример, имеется метрическое пространство, но на нем еще есть мера. И вы рассматриваете метрику как функцию двух переменных. Вот я и спрашиваю, а что это такое функция распределения метрики как функции двух переменных? Вот об этом пойдет речь. В частности, вот я первый пункт назвал метрические тройки и энтропия. Хочу сказать, что только что вышел, значит, этой темой я занимаюсь последние лет 20. Вот только что вышел в успехах наш обзор с моими учениками Затицким, Вепревым, но еще были до этого работы с Петровым, так что можно подробнее посмотреть по этим статьям. Там указана большая литература. Так вот, я сначала расскажу о метрических тройках, об особой энтропии, затем определю, что такое матричное распределение, и скажу, что такое инвариант метрики, классификация метрик на пространстве с мерой. Это теорема Громова-Вершика. Затем я перейду от метрик к общим измеримым функциям, где ситуация чуть сложнее, и ответ, в общем, получен гораздо позже. После этого я займусь совсем кратко, хотя это, может быть, сказать, главная тема нашего обзора, это идея, как применить эти методы, а именно метрики, в эргодической теории. Сразу хочу сказать, что новизна здесь в том, что вопреки традиции, когда в эргодической теории, вообще в теории процессов все концентрируется около вероятности, на самом деле введение метрики кажется чуждой для этой особой теории, например, для теории стационарных процессов. На самом деле очень полезно, и самое главное, ее роль этой метрики состоит в том, чтобы сформулировать некоторые определения и принципы, а потом доказать, что от метрики они не зависят. Вот этот эффект я называю по аналогии с химией каталитическим эффектом. Значит, метрика как катализатор. Она сначала присутствует для того, чтобы мы поняли смысл инвариантов, потом оказывается, что она от нее ничего не зависит. Ну и последнее, это совсем свежая работа наша с Петровым, которая открывает целый, можно сказать, круг. Я говорю опять по-русски. The last paper, recent paper in archive about spectrum of matrix distribution, this is maybe first step in the very new and very important direction. So the first item, metric triple means triple space, measure, and metric, such that X mu is standard measure space, which is isomorphic to, say, unit interval with Lebesgue measure. A measure always will be continuous without atoms. But of course, you can consider general case. Then X rho is separable complete metric space. So this is very common situation which consider, how to say, step by step, either as measure, either as metric, but only Gromov and me in the beginning of 2000s discuss about the general consideration of both structures. It's not trivial to say about these things. Why? Because if you consider metric as function on measure space, you must suppose that all inequalities, positivity and triangle inequalities, satisfied only almost everywhere. Say, symmetry rho x y equal to rho y x means that this is true for almost all pairs. The same with triangle inequality. But we have a happy solution of this problem because we can prove that for each such a triple with this property, there exists a set of measure one such that there exists concrete metric in usual sense on this set of measure one, which is equal up to measure zero to the initial metric, and of course it's unique up to isomorphism. So we can forget about these difficulties. We consider rho as usual metric on the some special set of full measure. Now, very important things which I want to emphasize, the notion of entropy. We call it MM, measure metric entropy. And this is a very interesting story. What does it mean? This is a function on epsilon, which is equal to logarithm for some foundation, it's not important, of a minimal set of points on space, such that measure of union of balls of radio less than epsilon has measure more than 1 minus epsilon. In general, you can consider this epsilon and another epsilon as different, epsilon delta, but this is not important just now. This notion, based on very natural and very simple lemma, which people never considered, I don't know why, because the finiteness of this set, why there is a finite number of such a K, based on the separability of our space. So this is a very important notion, which is, I emphasize, different from epsilon entropy of compact. And this is very important point of view. Unfortunately, this definition, in a sense, neglected by mathematicians, but in our theory, it's much more important than usual entropy, which based on probability entropy. I will soon write some special historical paper in which I try to compare approach of Shannon and Kolmogorov in the following sense. Shannon introduced entropy in probability sense and Kolmogorov used it in order to define entropy of dynamical system. This is well-known papers which start from which new era in dynamical system was open. But unfortunately, from other side, Kolmogorov considered epsilon entropy of compact, and this is a big theory by him and his pupils, and they didn't consider both together. What is very interesting, and this is we discuss, I will discuss in this my paper, but unfortunately I didn't know about this. Shannon was very was a very good, very I think deep observation that this definition of entropy also possible in his theory. Unfortunately, this is small remark in his well-known paper, and nobody except maybe a few guys consider this. But for others, it's very important. My definition of so-called scaling entropy based on this notion. Okay. Now let me explain.
Извините, а можно вопрос? Вот можно вопрос?
Да.
Относительно энтропии, функция h epsilon of tau, how it depends on axis, on the chosen axis?
The invariant is just asymptotic of this function when epsilon goes to 0.
For arbitrary sequence of x,
Sorry?
Minimum over x, in the
Minimum,
definition of
minimum k. K is number of points. How many epsilon net? What is an epsilon net? But epsilon net in this sense, that union of balls is not all space, but only measure of this union more than 1 minus epsilon. Do you understand?
Yes, question was it does not depend on x, on x1, xk. As a
We consider all possible choice of k points such that this inequality is true.
Thank you. Yeah.
Maybe if I have time, I'll tell you about connection with Shannon entropy more, but just now it's very important that such a notion as asymptotic to this function, this is element of metric triples. So this is canonical notion for metric triple. Now, what does it mean, metric distribution? This is very simple idea, which was firstly, I don't know, it's maybe funny to say that this is new idea, but nevertheless, in our consideration, it was important, firstly, in a book of Gromov and in the same time in my papers. We have some function of two variables, measurable function. And for example, this function could be metric. So, but this is a function on space X, really is a function on space X cross X. Now choose independent, infinite, identically distributed variables, xi1, xi2, xi(n), and so on. This is the variables on the space X. So we have an X and choose independently, step by step, countably many of points. Then we consider map, which put this sequence, Bernoulli sequence, xi1, xi2, and so on, to the infinite matrix. F xi I xi j metric with this ij. That's all. The definition is the following: this function, this measure. So what is the object? The object is just image of the Bernoulli measure on the space X infinity in space of all metrics, symmetric, for example, if function is symmetric function, symmetric matrices with infinite number of coordinates. So this is measure on the space of infinite, for if it's metrics, then distance matrices, and there's a two important property. The first one, this measure is ergodic and also invariant under the action of infinite symmetric group, which permutes simultaneously rows and columns of the matrix. It's trivial that this is the case of this image, because this property definitely true for Bernoulli system, and so we have image of Bernoulli measure in the space of matrix. Why it's important? Because the following theorem is true. This is theorem by Gromov and me. More or less, well, we have a very different proofs, but then I define this generalization of the theorem not from metric to, but for all measurable function. Sorry, this means rho I, it's sub I. So we have two triples, x1, mu1, rho1, and x2, mu2, rho2. Isomorphism between two triples means naturally existence of the isometry which preserves the measure. Theorem: two triples are isomorphic if and only if their metric distribution equal as measure. So we have two measures in space of infinite matrix, and we can say about our triple, in a sense, everything, all invariant questions has answer in terms of matrix distribution. There is a, let me say immediately that, for example, entropy and all other property of measured triples can be expressed sometimes very easily, sometimes not, in terms of matrix distribution. I want to emphasize that matrix distribution as measure in space of matrix is just right notion of analog of distribution of function of one variables. Of course, you can consider maybe other things, but for me, it's clear that this is a right notion. The following, this theorem can be, as I told, generated by all measurable functions of two variables. If you have two, but again, we can say, as I told about one variables, we have some restriction on multiplicity of values. I called function is pure if for each two variables partial function are different, not equal. This is the same as to say that function has all is up to measure 0, 1 to 1. So for this function, of course, general case can be reduced to pure function. But for pure function, we have general theorem, which is analog of Gromov-Vershik theorem. But now f is not metric, but arbitrary measurable function. Well, I want to say that really it's important that this function are from L1. I just now my proof concern only this case because it deeply use ergodic theorem. But my impression that is true for all measurable function. What is very important that the matrix distribution is measure on infinite matrices, but it's very different from say GOE and GUE because this is completely different type of measure on the matrices, and I will tell about later. So the proof of the theorem I even give you. So for metric we have very nice definition proof, which well, from the proof of Gromov was very complicated and analytic. My proof is used ergodic theorem and very natural. But why metric is special case? Because of very important things. If you have measure space with metric, and suppose you have dense countable subset of your space. But of course, dense subset is also metric space. And because if this countable subset is dense, you can restore by operation of completion of the discrete space and obtain all space as limit. So this this is why the proof for metric is more or less very nice and very short. Of course, to say about measure, you need some ergodic theorem, but measure, what is important that dense set restore all space. This is not true for function, but the real the end of the story is the same as for case of metric. What is very interesting, what kind of measure on space of metrics we have. As I told, this is far from to be GOE and something else. I have some notion of dense measure, which is equivalent to B matrix. So we have the following question: what kind of measure on space of matrices is matrix distribution of some measurable function? The answer is I have answer which called dense measure, but unfortunately, in order to say about this, I need some special operation for which I have no time to explain. But nevertheless, this operation show us that GOE is not, I call such a measure simple, is not simple. And simple measure is very special case in sense some kind of compact measure in the space of matrices. Now let me say about yes, in this point I want to mention some important and old papers by Aldous, which consider the following question: to the generalization of well-known theorem by definition how to explain what kind of measure on the space of matrices, for example, symmetric matrices, which is invariant with respect to simultaneous permutation of rows and columns, and of course ergodic. This is his proof was very complicated, but the main idea was that there is two cases, roughly speaking, one close to case of the GOE, when all coordinates of matrix are independent, and other, and this other is just my simple measure, but there is no such a simple description as I have now in that sense. This is important difference, and the reason why we have, roughly speaking, of course, these two cases can be mixed. It's not true that this is the direct product of two measures, but in a sense it's tensor product. But why only these two? And this is very deep question. And my conjecture is the following. This is true because the following hypothesis is must be true. Namely, if you look at the group of all action of symmetric group, which simultaneously permute rows and columns, this is infinite symmetric group. Then my impression that this is maximal group in the group of all possible permutation of the coordinates of the symmetric matrices. This is only conjecture now, a new conjecture, and my impression that just this very deep fact, definitely it's very complicated question. Even for finite case, it's unknown, as I know from specialists in theory of finite group. It's a very strange, but the final analog of my question is unknown up to now. But of course, it's very complicated form, infinite case. And this alternative to have only all group or this group of simultaneous permutation is just explanation why we have only two type of measures. Now let me say about statistical sum. This is completely different things which I started some years ago, and let me say a few words about this. So we again have metric triple, but now we have also some measure preserving automorphism T. And we study as an ergodic theory property of this automorphism, but we have another guy, rho, which is not, which people didn't consider. This is not bad to have this triple because we can organize statistical sum of metric. Look here, omega T of Z is just metric, which is infinite sum. This is some multiplication, and this is nothing more the image of our measure metric rho under transformation T. So we have this sum, power sum of this metric, and the Z change between 0 and 1. We interest what happened when Z close to 1. So now we have on our space not one metric, but only deformation of metric. And the following extremely interesting and non-trivial questions appeared. First of all, okay, we have metric. As you have heard, each metric has entropy, entropy. So for each Z, you have some entropy of this metric space with this iterated metric. And it happened that asymptotic, which I called before, this is function on epsilon. And for typical T, it happened that this asymptotic of epsilon doesn't depend on epsilon. So we have, in a sense, a property of entropy and even asymptotic of entropy, which doesn't depend on initial metric. This is my conjecture, which was proved by my pupil, firstly for special case T, and later it happened that another member of our team, young mathematician Yegor Veprev, proved that sometimes it's not true, that it's not the same asymptotic for all epsilon. So we have two parameters. One parameter epsilon or delta. Here I simply change Z to delta. It's not important. But it happens that sometimes asymptotic hardly depend on epsilon, and you need several types of asymptotics. But nevertheless, still it's true that this more complicated asymptotic doesn't depend on initial metric. So we have in ergodic theory some new situation. We have new invariants which contain the Shannon-Kolmogorov entropy as very special case when these asymptotics are in a sense linear. But we have all other asymptotics. This is close to previous investigation by Kushnerenko, Katok, and Tuvino, but nevertheless, such an idea about statistical sum, I think, more adequate to our problem. So, unfortunately, I must finish, I think. Let me say, so this is what I mentioned.
You still have time. You have an hour, you have the whole hour, so you still have 20 minutes. You can talk as
sorry. So I have 30 minutes. That means now it's 3:10. Okay.
Yes.
Okay. In this case, I can tell you more in more detail. So repeat once more. We have sequence of deformation of metric, and for each such a metric, we define entropy, and this is entropy of this triple. So we have several deformation of metric, and so deformation of asymptotics. And as I told, in general, these asymptotics not the same. There exists such a T for which can't be described by unique asymptotic of epsilon. You need some scale, several scales of epsilon, or in another word, two parameter epsilon and delta. But this is detail which is written in our survey, but nevertheless it's not important. What is important that these asymptotics, hard or not so hard, doesn't depend on metric. This is why I call it catalytic invariant, because as I told, we introduce metric and using this metric for definition of deformation, and after all, we obtain result that asymptotic doesn't depend on rho. As I told that this is analog of a role of catalysator in the chemical reactions. Well, there is many problems close to new entropies. I told this is generalization of the Kolmogorov-Shannon entropy in very, how to say, rich area, because instead of positivity entropy in Kolmogorov theory, we have a huge of different asymptotics. Unfortunately, we have such a there is a theorem that, roughly speaking, all asymptotic realized for some automorphism, but up to now, very few automorphism which is different from well-known use this kind of asymptotic. So I want to say that there are a lot of possibilities, but in some practical theory, we use only few of this kind of asymptotics. I hope that in general it will be clear, more clear later. One of the main problem to describe that T, which I mentioned before, for which there is no one epsilon asymptotics, and you need epsilon and delta asymptotic. This kind of automorphism I called non-stable, and if you have only epsilon stable, the definition of non-stable automorphism firstly was done by Veprev, and up to now we have no good approximation of such an automorphism. I am sure that this is completely new kind of dynamical system, and hope that we have progress soon. Now, let me say about this is what a theorem which I already done. Now, return back to matrix distribution, and I want to describe only one problem of many of such problems, which close to spectrum of random matrices. So, as I told, matrix distribution is nothing more than a measure in the space of metric. Let's consider symmetric function. So we have as matrix distribution measure in symmetric matrices. For example, real symmetric matrices. So we have class of real symmetric matrices, which I call simple. This matrix invariant with respect to simultaneous permutation of row and columns, and ergodic. And there is another property which distinguishes these measures from GOE and so on. But let's consider such a matrix distribution and put the following question. Unfortunately, I had no time to describe in some denotation, but let me say on the word, by the word. So you have matrix, and then this metric sometimes can be considered as metric of some operator. Let me say for specialists as Vadim MALYSHEV and other in spectral theory, in terms of this theory, you have operator on the space of function of one variables. I don't want to describe the space of functions, but this operator has kernel. And moreover, let's consider that this kernel is metric. I'm not sure that people know very much about this case. I asked some specialists in spectral theory in St. Petersburg. Unfortunately, it's not so clear. So suppose we have metric even on the real line, and consider operator with kernel this metric. And firstly, let's consider this this metric is integrable with square. In a sense, it means that integral of rho square d mu is finite, which means that operator is Hilbert-Schmidt, and for this case there is a theorem by Kolchinsky which is very important, but this is what I want to, in a sense, to give a new step from this case. His case is the following: if you have Hilbert-Schmidt symmetric matrices, infinite matrices, and then consider main minors of this matrix of order 1, 2, 3, and so on, and look at the spectrum. Of course, it's a symmetric matrix, so it has symmetric, it has a real spectrum. And then let's consider this spectrum with multiplicity 1, for example, or maybe you have some measure on the spectrum. Anyway, you have sequence of finite discrete measures of order n, discrete of order n equal to 1, 2, and so to infinity, and can consider the limit of such a measure on the finite spectrum. Kolchinsky theorem proves that the limit is nothing more than spectrum of that operator, because it's a Hilbert-Schmidt operator, so it has a discrete spectrum and well-known cases and so on. My question concern the metrics which are not square integrable. And in our recent paper with Petrov, which just now I several days ago put it in archive, and it was published in Functional Analysis, give the first counterexample to this situation. Namely, our example is the following, and I invite specialists in spectrum to look at this example and to try to generalize very, very weak step which we had. Namely, we prove the following, that if you have Cauchy distribution on a real line as a kernel of the operator, it's not integrable with square. And look at the sequence of the spectrum of minors, then the limit, we didn't know what is the limit, but we know that this is not deterministic limit as in Kolchinsky's theorem. In Kolchinsky's theorem, limit is just limit of operator. We prove in this example that for very simple functionals, limit functional, there is no deterministic limit. And this is very important. So, of course, we know many examples from theory of Gaussian measure on the space of symmetric matrices, semicircle law, and so on. Now we have completely different situation. This is simply metric space with measure. But metric is not square integrable, only integrable, that's all. And it happened that the limit of the spectrum of minors is not deterministic. We didn't know even what's the limit spectrum of operator. Maybe it's continuous, maybe not, probably continuous. But nevertheless, this completely different question for with respect to several classical considerations. So I invite to look at this kind of. In general, I want to say the following: that matrix distribution as a measure on space of symmetric matrices, which called matrix distribution, has information about our function, about our kernel. And this information could be very complicated, very different, starting from entropy to spectrum of limit spectrum of minors. This very close to problems about the central measure for some example in the theory of Gelfand-Zetlin operator, which we studied with Petrov also in previous paper. But there is a very interesting area. I want to say that the main problem is to, in a sense, to have some kind of rough classification of metric spaces with respect to, in terms of metric distribution. I want, of course, to mention some classical paper by von Neumann and forget his co-author, well known, in which they try to consider for finite case what kind of spectrum has a metric. And this description was very poor, very small examples. And from point of view of simulation, I asked some years ago some group in France to consider such a metric distribution for very simple metric. And this is very interesting computer effects, which has no up to now serious interpretation. So thank you very much for your attention.